Hello. Today we would discuss a very common real-life scenario where piping engineering skills and design techniques can be used to meet customers' requirements. Who would be the target audience of my presentation? Engineering designers of any form across the globe can use these design tips. Engineering departments can outsource work of this nature to me. Any student of hydraulics can use this information in academic projects on piping engineering. This presentation endeavors to encompass the basic design principles of a community water distribution piping system. In case you happen to be an affected dweller or an engineer seeking some tips or designing a new system or rectifying an existing system, this small presentation may be of interest. But before we move on to the design details of community water distribution, let us review why it is required to have a properly designed community water distribution system. Here are some of the common shortcomings. Water distribution piping in an apartment complex is sometimes finalized without proper engineering. Pipes and fittings available with regular erection contractor are often used. Also, improper sizes are selected for distribution piping. As a result, apartments farther away from water supply sources get penalized with water scarcity. Unreliable manual regulation of valves becomes inevitable to achieve equal water distribution. All these result in the relationship between neighbors getting tarnished. For achieving a good design, it is advised to follow a few basic checkpoints like larger pipe size for remote apartment inlets than the closer one, progressively reduced header pipe size from pump outlet maintaining optimum line velocity, conducting network flow analysis calculation to ensure fair distribution, for closed loops use of Hardy-Cross process, use of pressure breakdown orifice in preference to manual globe or water or butterfly valves if absolutely required, pump parameter selection criteria. Pump parameters needs to be selected in a way that pump flow is sufficient to replenish all consumers at a time, and pump head should include static elevation change, frictional head drop in pipes, valves, and fittings. Next, I will provide an illustrative example for a better comprehension of my assertions. It is assumed that the viewer is conversant with the basic pipe sizing theory. Refer to the schematic diagram below. The illustration represents a system where a pump set is employed to pump water from an underground reservoir through a piping distribution system to several overhead tanks belonging to the building of community owners. The reservoir is labeled as 1 and the overhead tanks as 2, 3, 4, 5, and 6. The table shows the elevation of the tank. The next few slides would show some illustrations and procedural details related to the diagram. Here are some of the basic points to be noted with reference to the schematic diagram on the previous slide. One pump is operating, other one is on standby. Valves and fittings are not shown. Breakup calculations for equivalent length for including effects of valves and fittings not shown. Pressure drop calculation by Hazen-Williams formula. Next few slides would describe the step-by-step process which the designer would need to execute to calculate the individual line pressure drops and derive the pump parameters. The first step would be to collect data on the following: desired flow to each consumer, static elevation of pump inlet reservoir, static elevation at each consumer storage reservoir inlet, optimum piping route to be followed from pump house to all consumer points. The second step would be to make a preliminary selection of pipe sizes as per the following guideline. Average velocity of 1 to 2 meter per second for pump suction, average velocity of 1.5 to 3 meter per second for pump discharge, distribution header, and consumption point inlet piping. Step 3 would be to conduct a flow calculation assuming a preliminary pump TDH and assigning desired flow for each consumer inlet and flow in the distribution header as required. The fourth step would be to note the deviation in the calculated pressure at the consumption point from the desired pressure. Step 5 is to conduct successive trials to narrow down the deviation as in step 4 as much as possible by varying the following as required to get an optimum result. Pipe size, flow to the consumption points, pump heads. In the next slide, I would describe the calculation. Here I am demonstrating a calculation with reference to the schematic diagram with some hypothetical data. Column 0 identifies the pipe. AB is the pipe suction from the reservoir. BC is the individual pump inlet. EG is the individual pump outlet, and so on. Column 1, 2, and 3 shows the pipe sizes. Nominal bore, pipe outside diameter, pipe thickness. Column 4 being the pipe components equivalent length. Flow in individual section is in column 5 and elevation in column 6 and 7. Column 6 being the inlet height above datum and column 7 the outlet height above datum. Then this slide demonstrates the results of piping pressure drop calculation and derivation of required pump parameters. Inlet pressure is calculated in column 8, pressure drop in column 9, outlet pressure in 10, and average velocity in column 11. Pump flow at operating condition, which is the sum total of flow to all the above 5 tanks, is 104.5 cubic meter per hour. Pump total dynamic head at operating condition is the algebraic difference of pump outlet and inlet pressure, which is 99.15 meters of water column. So as mentioned in the beginning, this is a reference of a typical piping distribution system from a real life scenario. In case the listener is interested in design service of a system of a similar or larger magnitude, he or she may contact at the following email address with full technical details of the problem and piping topography drawing in Acrobat Reader. Commercial matters may be negotiated. My email address is consultant.piping1@gmail.com. I repeat, it's consultant.piping1@gmail.com. Thanks for listening.